The airspeed indicator needle trembles past 450 miles per hour, then 480, then numbers that exist beyond the red line that Supermarine engineers painted to mark the absolute limit of what a Spitfire can survive. Flight Lieutenant Jeffrey Quill feels the aircraft shuddering around him like a living thing in terror, the control stick vibrating in his hands with frequencies that suggest structural failure is not a possibility, but an inevitability measured in seconds rather than minutes. At 30,000 feet above the English countryside, he pushes the nose down steeper, trading altitude for velocity with the kind of reckless precision that separates test pilots from ordinary humans who possess adequate survival instincts. The dive angle approaches vertical. The Merlin engine screams protests that no mechanic has ever heard before, producing harmonics that speak of metal stress approaching molecular limits, of engineering tolerances being exceeded by margins that make previous safety calculations look like conservative suggestions rather than absolute boundaries. Jeffrey's altimeter spins backward through numbers that represent his rapidly diminishing options for recovery, but his attention remains fixed on instruments that measure what has never been measured before: how fast a Spitfire can actually fly when atmospheric resistance becomes the only limiting factor, when gravity provides unlimited acceleration, when every design assumption about maximum performance gets tested against the unforgiving mathematics of terminal velocity. This is not authorized testing. This is not approved experimentation. This is one pilot's private investigation into aerodynamic theories that his engineering colleagues considered dangerously speculative, pursuing answers to questions that official policy prefers to leave unasked because the experimental methods required to answer them exceed acceptable risk parameters by margins that make insurance companies nervous and commanding officers apoplectic. But Jeffrey understands that war changes the mathematics of acceptable risk, that desperation creates its own experimental protocols, that breakthrough discoveries often require the willingness to ignore expert warnings about what is and isn't safely possible when survival depends on finding solutions that exist beyond the boundaries of conventional wisdom. Britain, in 1943, occupies the precarious middle ground between catastrophic defeat and meaningful victory, sustained by industrial capacity that transforms civilian production into military advantage, scientific innovation that converts theoretical knowledge into practical weapons, and the particular kind of collective determination that develops when people understand that failure means not just political defeat, but cultural extinction. The Royal Air Force has survived the Battle of Britain through superior tactics, better pilot training, and aircraft that perform adequately against German fighters designed by engineers who understood that technical superiority could compensate for numerical disadvantage if achieved through systematic attention to aerodynamic efficiency and engine performance optimization. But adequacy is no longer sufficient. German aircraft development has produced fighters that challenge British air superiority through speed advantages that neutralize tactical skill, through performance improvements that make traditional combat maneuvers obsolete, through technical innovations that transform aerial engagement from pilot skill competition into engineering superiority demonstration. The Focke-Wulf 190 and improved Messerschmitt variants achieve velocities that allow German pilots to engage or disengage at will, to choose combat conditions that favor their aircraft's strengths while exploiting British fighters' limitations, to convert technical advantage into tactical dominance that threatens the air superiority upon which British survival strategies depend. The Spitfire Mk IX represents the latest British response to German technical challenges, incorporating engine improvements and aerodynamic refinements that restore competitive parity in most flight regimes. But competitive parity is not technical superiority, and technical superiority is what Britain requires to maintain control of European airspace, while simultaneously supporting invasion preparations that will depend on air dominance so complete that German resistance becomes tactically impossible rather than merely difficult to overcome. The question facing British aircraft designers is not how to build fighters that match German performance, but how to build fighters that exceed German capabilities by margins large enough to provide decisive tactical advantage despite numerical disadvantages that will persist until American industrial capacity reaches full wartime production levels. Jeffrey Quill possesses the particular combination of aeronautical engineering education and practical flight experience that allows some test pilots to see solutions where others see only problems, to recognize opportunities disguised as dangerous speculation, to understand that innovation often requires experimental methods that exceed safety margins established by people who prioritize institutional liability over breakthrough discovery. His formal training at Cambridge provided theoretical foundation in fluid dynamics and structural engineering that enables him to evaluate aerodynamic hypotheses through mathematical analysis rather than simply accepting conventional wisdom about aircraft performance limitations. His operational experience flying Spitfires in combat conditions has demonstrated that actual aircraft performance often exceeds engineering specifications when pilots understand how to exploit design characteristics that theoretical analysis failed to predict. The theory that Jeffrey tests during his unauthorized high-altitude dive emerges from careful analysis of German fighter performance data gathered through combat observation, intelligence reports, and examination of captured aircraft that reveal engineering approaches significantly different from British design philosophy. German engineers appear to prioritize high-speed performance over low-speed maneuverability, accepting decreased agility at typical combat velocities in exchange for superior performance at maximum speed that allows tactical advantages unavailable to aircraft optimized for traditional dogfighting scenarios. But British engineers dismiss German design choices as strategic mistakes, arguing that combat effectiveness depends on maneuverability rather than maximum velocity, that pilot skill matters more than aircraft speed, that traditional air combat tactics remain valid despite changing technical capabilities. Jeffrey suspects that British engineering conservatism is preventing recognition of aerodynamic possibilities that German designers have begun exploiting, that conventional wisdom about fighter aircraft performance is based on assumptions that technological development has rendered obsolete, that breakthrough improvements in Spitfire performance might be achievable through modifications that current design philosophy considers unnecessary or counterproductive. His hypothesis focuses on high-speed flight characteristics that British engineers have never systematically investigated because official testing protocols emphasize operational safety over experimental discovery, because institutional procedures prioritize incremental improvement over revolutionary innovation, because traditional test flight methodology assumes that exceeding design limitations provides no useful information about potential performance improvements. The dive begins at 32,000 feet, altitude that provides sufficient vertical distance for extended high-speed testing while maintaining adequate recovery margin if control problems develop during experimental maneuvers that push aircraft performance beyond documented limits. Jeffrey configures his Spitfire for maximum aerodynamic efficiency, retracting landing gear and flaps, adjusting propeller pitch for high-speed operation, setting engine controls for maximum power output despite manufacturer warnings about sustained operation at settings that exceed recommended parameters. The preliminary acceleration occurs gradually, building velocity through gentle nose-down attitude that allows systematic observation of aircraft behavior as airspeed increases beyond normal operational ranges into territories that no Spitfire pilot has explored systematically. At 400 miles per hour, the aircraft performs normally, responding to control inputs with familiar characteristics that match engineering predictions and pilot expectations developed through hundreds of hours of operational experience. At 420 miles per hour, Subtle changes in control indicate aerodynamic effects that approach the boundaries of documented flight envelope. But aircraft behavior remains predictable and manageable despite operating at velocities that exceed typical combat speeds by significant margins. At 440 miles per hour, control surface effectiveness begins changing in ways that suggest airflow patterns around the aircraft are transitioning from attached flow to separated flow, creating aerodynamic conditions that British engineers have never studied systematically because official testing protocols prohibit sustained flight at such extreme velocities. Jeffrey increases the dive angle, trading altitude for acceleration with systematic precision, monitoring instrument readings that document aircraft performance in flight regimes that exist beyond the boundaries of approved testing procedures. The airspeed indicator continues climbing past numbers that represent theoretical maximums established through wind tunnel testing and mathematical analysis, entering ranges where experimental data does not exist because previous test pilots have lacked either the technical curiosity or institutional authorization to investigate performance characteristics that exceed safety margins by substantial amounts. But the aircraft continues flying, continues responding to control inputs, continues demonstrating that actual performance capabilities exceed engineering predictions by margins that suggest fundamental misunderstanding of aerodynamic possibilities rather than simple conservative bias in safety calculations. At 460 miles per hour, Jeffrey discovers that Spitfire control characteristics change dramatically but predictably, that high-speed flight requires different control techniques but does not produce uncontrollable flight behavior, that aircraft stability actually improves at extreme velocities despite engineering theories that predict increasing instability as airspeed approaches structural limits. The revelation transforms his understanding of fighter aircraft capabilities, suggests that British fighters have been artificially limited by conservative engineering assumptions rather than actual aerodynamic constraints, indicates that substantial performance improvements might be achievable through operational techniques that exploit high-speed flight characteristics that conventional wisdom considers too dangerous for routine implementation. The control surfaces that feel sluggish at normal combat speeds become remarkably effective at extreme velocities, providing precise aircraft control through small deflections that produce large changes in flight path despite operating in aerodynamic conditions that theory suggests should reduce control authority to marginal levels. The engine that struggles to maintain power at typical operational altitudes performs remarkably well in the dense air encountered during high-speed descent, producing thrust levels that exceed sea-level specifications despite operating at power settings that manufacturer documentation considers potentially damaging when sustained for extended periods. But most importantly, Jeffrey realizes that the Spitfire maintains structural integrity at speeds that exceed engineering specifications by margins so substantial that previous safety calculations appear to have been based on overly conservative assumptions about material properties, stress distribution, and failure modes that occur primarily in theoretical analysis rather than actual flight operations. The aircraft that supposedly approaches structural limits at 400 miles per hour continues flying normally at speeds approaching 500 miles per hour, demonstrating that actual design margins provide safety factors much larger than engineering documentation suggests. The recovery process requires careful planning and systematic execution, trading velocity for altitude through gradual attitude, changes that avoid imposing structural loads that might cause failure despite successful high-speed flight testing. Jeffrey begins pulling out of the dive at 15,000 feet, using gentle control inputs that spread deceleration forces across extended time periods, monitoring structural stress indicators that suggest the aircraft tolerates recovery loads well within acceptable limits, despite previous operation at velocities that engineering theory considers structurally dangerous. The successful recovery demonstrates not only that extreme high-speed flight is possible, But that transition back to normal flight operations can be accomplished safely using appropriate techniques that respect aerodynamic realities rather than simply following procedural guidelines based on conservative engineering assumptions. When Jeffrey lands and reports his experimental results to engineering teams responsible for Spitfire performance optimization, the initial response combines disbelief with institutional anxiety about unauthorized testing that violates multiple safety protocols and exceeds approved experimental parameters by margins that make official sanction difficult regardless of technical value. But the data he provides documents aircraft performance characteristics that contradict fundamental assumptions about fighter aircraft capabilities, suggests modification possibilities that could provide substantial tactical advantages, demonstrates that breakthrough improvements might be achievable through relatively simple changes to operational procedures and design specifications. The engineering analysis of Jeffrey's high-speed flight data reveals that Spitfire aerodynamic design includes characteristics that were never fully exploited because testing protocols prevented systematic investigation of extreme performance conditions. That aircraft structural strength exceeds engineering specifications by margins that allow safe operation at velocities previously considered impossible. That engine performance optimization for high-speed flight could provide substantial improvements in maximum velocity without requiring major design modifications or manufacturing changes that would disrupt production schedules during critical wartime periods. The modifications that emerge from Jeffrey's experimental data focus on aerodynamic refinements that reduce drag at high speeds, engine tuning that optimizes power output for extreme velocity conditions, and structural reinforcements that allow sustained operation at performance levels that previous design philosophy considered temporarily achievable but operationally impractical. The changes appear minor compared to the performance improvements they enable, suggesting that British fighter aircraft have been operating substantially below their actual capabilities due to conservative engineering assumptions rather than fundamental design limitations. The first modified Spitfires demonstrate performance improvements that exceed engineering predictions, achieving maximum velocities that surpass German fighter capabilities by margins sufficient to provide decisive tactical advantages in combat conditions where speed determines engagement outcomes. The high-speed flight characteristics that Jeffrey discovered during his unauthorized experimental dive proved to be consistently reproducible, teachable to operational pilots through systematic training programs, and strategically valuable for mission profiles that require rapid transit through contested airspace or pursuit of high-performance enemy aircraft that previously could escape through superior speed. But the tactical implications extend beyond simple performance improvements. Spitfires capable of extreme high-speed flight can execute combat maneuvers that were previously impossible, can engage or disengage from combat at will rather than being forced to accept unfavorable engagement conditions, can exploit altitude and velocity advantages that transform traditional air combat from pilot skill competition into systematic application of technical superiority. The psychological effect on German pilots proves equally significant, as British fighters that were previously considered technically inferior begin demonstrating performance capabilities that challenge German assumptions about air superiority based on aircraft specifications rather than operational effectiveness. The production modifications that incorporate Jeffrey's discoveries into standard Spitfire manufacturing prove implementable without major disruption to existing assembly procedures, requiring primarily changes to engine calibration, aerodynamic detail refinements, and pilot training programs that teach high-speed flight techniques through systematic curriculum development rather than dangerous individual experimentation. The engineering teams that initially resisted Jeffrey's unauthorized testing eventually acknowledged that his experimental methodology, while violating safety protocols, provided technical insights that conventional testing procedures would never have revealed due to institutional bias toward incremental improvement over revolutionary discovery. The strategic impact of improved Spitfire performance becomes apparent during subsequent air operations over occupied Europe, where British fighters demonstrate air superiority margins that allow tactical freedom previously unavailable due to German technical advantages. The speed improvements that seemed modest during initial testing proved tactically decisive when applied systematically across entire fighter squadrons, creating cumulative advantages that transform air combat from competitive engagement into systematic dominance of European airspace during critical periods of invasion preparation and strategic bombing campaigns. Jeffrey's unauthorized experimental dive, which initially appeared to be dangerous individual initiative that violated institutional safety protocols, proves to be the catalyst for aerodynamic discoveries that influence fighter aircraft design throughout the remainder of the war and beyond. The high-speed flight techniques he developed through personal experimentation become standard operational procedures taught to combat pilots. The performance improvements he discovered through individual initiative become incorporated into official aircraft specifications. The experimental methodology he employed despite institutional disapproval becomes the foundation for systematic test flight programs that investigate aircraft capabilities beyond conservative engineering assumptions. The theoretical framework that Jeffrey challenged through practical experimentation, the assumption that aircraft performance limitations are determined by engineering calculations rather than actual flight testing, proves to be fundamentally flawed based on mathematical models that prioritize safety margins over performance optimization, institutional procedures that emphasize risk avoidance over breakthrough discovery, engineering conservatism that prevents recognition of possibilities that exist beyond conventional wisdom about aerodynamic limitations and structural constraints. Years later, when jet aircraft development requires systematic investigation of flight characteristics that exceed all previous experience with propeller-driven fighters, aviation engineers study Jeffrey's experimental methodology as an example of how individual initiative can produce breakthrough discoveries that institutional procedures would never achieve, how dangerous experimentation can provide essential technical insights when conducted by individuals who understand both theoretical principles and practical limitations, how breakthrough innovation often requires willingness to ignore expert warnings about what is and isn't safely possible when survival depends on finding solutions that exist beyond the boundaries of conventional engineering wisdom. The airfield where Jeffrey conducted his unauthorized high-speed testing remains active, supporting continued aircraft development that builds upon the experimental foundation he established through personal investigation of aerodynamic theories that his engineering colleagues considered dangerously speculative. But the principles he demonstrated, that actual aircraft performance often exceeds engineering specifications, that breakthrough improvements require experimental methods that exceed established safety margins, that institutional conservatism can prevent recognition of possibilities that individual initiative can discover. These lessons continue influencing aviation development across military and civilian applications that require systematic exploration of performance boundaries that theoretical analysis cannot predict accurately. The dive that began as unauthorized personal experimentation became the foundation for aerodynamic discoveries that transformed British air superiority from competitive parity to decisive advantage, demonstrating that innovation often emerges from individual willingness to test theories that institutional wisdom considers too dangerous for systematic investigation. Jeffrey's refusal to accept engineering limitations as absolute constraints proved that breakthrough performance improvements were achievable through modifications that conventional design philosophy had never considered, that revolutionary advances often require experimental methodology that exceeds safety protocols established by institutions that prioritize risk avoidance over performance optimization. The Spitfire that emerged from Jeffrey's high-speed testing proved capable of performance that exceeded German fighter capabilities by margins sufficient to restore British air superiority during critical periods, when technical disadvantage threatened strategic objectives that depended on absolute control of European airspace. The speed improvements that seemed dangerous during experimental testing proved essential for combat effectiveness that determined the outcome of air operations that influenced the entire course of strategic bombing campaigns and invasion preparations that ultimately decided the war's conclusion in favor of Allied forces, rather than German technical superiority. If stories like this remind you that breakthrough innovation often requires willingness to ignore expert warnings about limitations, that revolutionary advances emerge from individual courage to test theories that institutional wisdom considers too dangerous, then perhaps there are other moments when refusing to accept engineering constraints as absolute limitations created discoveries that changed how we understand what human ingenuity can accomplish when survival depends on finding solutions that exist beyond the boundaries of conventional safety margins and conservative design philosophy.